This was recorded for the Lectures for Change series, hashtag Lectures for Change, but unfortunately the sound didn't work, so I'm doing an overt voice now. I saw a demonstration using two bottles, one containing carbon dioxide and the other one not, on the internet, demonstrating the greenhouse effect. As the infrared light going through the bottle is absorbed by the carbon dioxide and water in there, and that bottle becomes warmer than the other one, it shows that some gases can absorb light more effectively than others can. This connects to the topic that we were talking about in this set of lectures, which is physical chemistry infrared absorption, where polar molecules can absorb light more effectively than non-polar molecules. There's a quantum mechanical rule that allows dipolar molecules to absorb infrared light more effectively, and those type of molecules are carbon dioxide and water. In fact, water, being an unsymmetrical molecule, is much more effective at absorbing infrared light than carbon dioxide is, and that exposes one of the things about the demonstration that are not obvious, that the water inside the bottle is more effective probably than the carbon dioxide. In the original version, the bottles are side by side like this, with a fizzy tablet causing carbon dioxide and water to be blown up into the air, and a bit of water in the other one to have the same thing in both. The light comes from the front to be the same amount of light on both. This is not exactly the same situation as the greenhouse effect, which is where short wavelength light comes onto the Earth, is absorbed by something on the ground, re-emitted at longer wavelength, and then is reabsorbed by carbon dioxide in the atmosphere or water. In fact, this is the basis of some of the criticism of the greenhouse effect, because a typical greenhouse has a reflective coat on the panes of glass which reflects the infrared light back towards the soil, making the whole greenhouse warm. This doesn't happen in the greenhouse effect using gases, because there isn't a pane of glass in the sky reflecting the light. In my version, two of the bottles have a black paper absorber in, which absorbs the visible light and converts it into infrared, preventing it from going right the way through the bottle and behaving like the surface of the Earth. The light cannot penetrate straight through the bottle unchanged. It has to be absorbed by the paper to get through at all. This makes it a little bit more like the situation on the Earth, although obviously there are still limitations. The temperature is measured by thermocouples in the lids of the bottles, which are all connected to the same program and give out a temperature reading. The bottles are not completely sealed in my case, but they hold a little bit of air. It's unclear to me whether the original demonstration had different pressures in the bottles as they got hotter and hotter. In my bottles the pressure does go up by a little bit, but it probably doesn't go up very much. What I'm about to do is take some calcium carbonate and react it with some hydrochloric acid in a small glass container, making carbon dioxide and a little bit of water vapor, maybe a little bit of hydrochloric acid vapor, and putting that through a little tube into the two bottles that I want to contain carbon dioxide and water. The other two are kept dry, although in the first version, the live version, it didn't work quite so well because one of the bottles that was supposed to be dry was actually wet. I repeated the experiment afterwards, which you can see very shortly after this, because also this video cuts off weirdly very soon after the start. What we'll see, so now I'll go faster to do that. Here I am at high speed, filling up my bottles, making some carbon dioxide, setting it all up. It all took a really long time in the lecture. This is always a problem with demonstrations. It's one of the reasons why I don't like doing them. As you can see, taking a really long time. This is at 4 times speed, still taking a long time. I still have to fill up the second bottle. Did this every time. It's a little bit tedious, I know, but never mind. And here we go. So that's one. The next one. Don't know what I'm drawing there. Oh yes, I'm writing down which one's which. To remember, good experimental technique. Cleaning my flask, it had plenty of carbon dioxide left. Giving it a shake. Bit more acid. Another shake. And connect it up. Set the measurement running at normal temperature so that I get the baseline, and then turn it on. All of them increase in temperature, and we will now switch to the other one. So this is a working version where the bottles are dry. The top scan is with a piece of paper and carbon dioxide in the bottle. The blue scan is with just carbon dioxide. The bottom two scans are with a piece of paper and without a piece of paper, with normal air in the bottle. As you can see, with the piece of paper and carbon dioxide we get the highest greenhouse effect in inverted commas. With just carbon dioxide we get some kind of effect, and without either we get no effect at all, or we get pretty much no effect whether the paper's in there or not, which is interesting. At some point I'm going to turn the light back off just to be sure that I'm disclosing this properly. This is at 10 times normal speed, so it takes a long time to do this. This is 10 minutes. At some point this is turning off. The highest temperature is about 44 degrees. The other bottles reached about 35 degrees, something like that, 32 degrees, depending on which ones they were. So now it's about to go, and I'm about to switch it over. Come on. I think I switched to slow motion. Here we go. Switch back to normal speed. Turn the light off. Come back and zoom back in and switch back to 10 times again, because this isn't any faster. The scale is linear, the time scale is linear, so is the temperature scale, but the zero isn't zero. So here they are coming back down again. What's also interesting is that the carbon dioxide and paper one comes down faster. That's possibly because it can also radiate infrared more effectively than the one without carbon dioxide and water in it. But it is also hotter, so it will lose heat faster. It's a little bit hard to analyze. What we do see, however, is that it crosses the temperature of the other ones, which suggests that it's better at losing heat than the others, which is logical. There is a little problem with the offset of the thermocouples on this experiment because I didn't set them up properly. So here's the graph a bit nicer. The axes aren't labelled, unfortunately, sorry about that. The bottom is time, the vertical axis is temperature in centigrade. I hope this was entertaining, and go and see other lectures for futures under the hashtag lectures for future.